Sure, but sure, they're weighted differently, but what does that? So if you have to like tell me exactly what this corresponds to in this image. So if I move this away from y-axis, far away, will Q10 change? So if I just move the image along y-axis, Q10 will not change because the y does not appear. But the Q is, if I change along the x-axis, yes.
So we could say that Q01 represents the distribution of galaxies along the y-axis, and Q10 represents the distribution of galaxies around the x-axis.
What do you mean by distribution?
Or maybe the comparison between Q01 and Q00 give us somehow an idea of how galaxies are distributed around, or I don't know.
So we're talking about one galaxy. So what
just
do you mean
one
by
galaxy?
Distributions of galaxies.
Okay. So we're talking just about
just
one
galaxy. One galaxy
okay.
in a very big image where the origin is at the center. The flux is the same no matter where I place the galaxy.
Correct.
But the Q01 and Q10 changes. So what could it possibly mean when I move this galaxy?
It will tell us where the galaxy is?
Yes, exactly. It gives you the center of this galaxy. If the center of this galaxy is exactly at origin, Q10, Q00 will be zeros again. Because one of them, I'm also assuming it is symmetrically distributed, or for now say these are perfect circles. And Q10 and Q01 will tell the y coordinate of the center of the galaxy and the x coordinate of the center of this galaxy.
By themselves or comparing them to
Q00? Yes. So because Q10 can just change if the brightness of the galaxy itself changes. So typically so this is the position of the center of the galaxy, x0 and y0. x0 would be defined as Q10 divided by Q00, and y0 will be Q01 by Q00. You have to divide by Q00 to take into account that this quantity can change if the flux changes, if the total brightness changes. But the x0 and y0 shouldn't change. So the 00 or the zeroth moments tells about the flux of the galaxy, how bright it is. The Q01, Q10 when compared to the total flux tells you where the galaxy is. Yes.
So that Q01 and Q10 would be like the expectation value of the variables of the position x
yes.
and the position y.
Yes, that's
right?
correct. Yes.
Of course.
So you can imagine I of x as a probability distribution. So you can imagine this galaxy's light as some probability distribution, and x and y can tell you the expectation value of this variables x and y. So if you call this x and y as random variables given by this probability distribution, x0 and y0 will tell you the average values of those random variables. Another way to see this is if I of x is two-dimensional density, a mass density, x0 and y0 gives you the center of mass of this distribution.
But that is not necessarily the point where you get the most, the brightest point in the galaxy. I mean,
not necessarily.
No.
if the galaxy is like say a Gaussian profile, then yes, but not necessarily. So the easiest way to think of it as this as some mass distribution, and x naught and y naught tell you the center of mass of this system of particles. So we call these as the centroid. So they are not necessarily the center part, they are not necessarily the brightest part, but it's an indication of where in this image the galaxy is. So, and then the second moments is where the I plus j is 2. So in this case the I plus j is 0, so we call this 0th moment. We call these as the first moment since the sum is 1. There will be 3 second moments corresponding to 0, 2, 1, 1, 2, 0, and they tell you how distributed this galaxy is about its own center. So I'm going to assume that we will now place the galaxy always at the center, at the origin. Otherwise you should have to subtract this x naught and y naught from x and y in the definitions. But we will assume that the galaxy, the center of the galaxy is the origin. Then one way of defining ellipticity is to have a structure very, very similar to this. So we will say that the real part of the ellipticity is q20 minus q02, and the imaginary part is 2q1. So this would mean that the epsilon, which is the ellipticity, is integral dx dy x squared minus y squared times xy. So this will be the real part, and then the imaginary part is dx dy 2xy. So if you see the structure keeps repeating, whether you are in Fourier space, you're talking about k space, it can be k1 square minus k2 square, or it can be an x squared minus y squared integrated, and this epsilon 2 is always the cross term. So in fact the moments act like the Fourier modes themselves in some sense. So these are just convenient definitions that help us see how the distributions are. So by distribution I mean how is the light diffused or distributed around this center of the galaxy itself. And again you should also divide this quantity by something else so that you are not dependent on flux. If you increase the flux keeping the shape the same, the ellipticity should not change. So one common and but somewhat ugly way of defining this normalization is with this denominator. So you don't have to worry why exactly this denominator is there. It is such that this epsilon has some other nice properties. There is another definition of ellipticity where you only have these two, you don't have this. So there are different definitions of ellipticity. I'm just considering one particular definition of ellipticity. And if the image of the galaxy really happens to be an ellipse, then this definition is equivalent to the other definition that we had before, which is this. So for a perfectly elliptical galaxy, you can define the ellipticity either this way or this way, and you would end up with the same answer. But the advantage that this has is, even if the actual galaxy is not an ellipse, you can always compute these quantities, you will get a number. They might not be very meaningful, but at least you have something from which you can proceed. You are able to define the ellipticity in some way. And this is not too bad because it gives you back the other definition of ellipticity when that is the case. is the definitions and is it clear? So it may not be very meaningful yet, but you should know that these moments tell you something about the distribution. So it can tell about the flux, it can tell where is the galaxy in an image, and the second moments will tell you how different the galaxies are. For example, if so this is actually a measure of the size itself, Q02 plus Q20. So Q20 plus Q02 and divided by Q00 is so this is a measure of size of the galaxy. Now if you have a larger circle, now assume that the galaxies are circles again. This would be large if the circle is larger. So in some sense this is like the radius of the circle. And a smaller galaxy would have a smaller value for this quantity. So another way of seeing this is, let's imagine I of xy to be Gaussian, to be a two-dimensional Gaussian. Can I erase this part? So so let me first draw a one-dimensional galaxy for visualization. This x. So if f of x is some constant times exponential of minus x squared by 2 sigma squared. So this sigma is a size, is one way of defining the size. So a smaller sigma will look like this, and a larger sigma will look like this. So sigma equals, so I'm just saying roughly sigma is 10, it's not really 10, and this can be sigma equals 1. So Gaussian is technically infinite in size because it has a spread from minus infinity to infinity. So clearly saying infinity is the size is not a meaningful quantity, but then we can assign a size using this parameter sigma squared. And now you can define a two-dimensional Gaussian similar way. So you can say I of xy is some constant, say I00, exponential of minus x squared by 2 sigma squared. Now I will assume the sigma is same in both directions. Now if you do Q20, actually let's assume they are different. If you do this integral, then you will have x squared or minus x squared by 2 sigma x squared. So the I00 term cancels. You will get some normalization factor here. Or let's say, for convenience, I'm going to say that constant as 1. It's not exactly 1, it will depend on sigma y, sigma x and sigma y. And the numerator, after doing this integral, so the y integral will give you 1 again. The x integral will give you something like sigma x squared. So Q20 by Q00 will give sigma x squared, and similarly Q02 divided by Q00 will give sigma y squared. So these moments are successful in capturing the so-called sizes of the galaxies, the second moments. And if you define the appropriate combinations, you can also capture the ellipticities of the galaxies. Okay, now what do we do from these ellipticities? Now that we have defined, these second moments, since they also depend on x and y, they are coordinate dependent quantities. So if you keep everything the same, but if you choose a different x and y, the moments that you get are going to change. And they are going to change such that if A is now a transformation, linear transformation, then the moments before and after the transformation, so this is before the transformation, this is after the transformation, are related this way. So if it is the, yes, sorry.
A over there is the Jacobian?
Yes,
The one we've been working with.
yes. So, and here by Q I only mean the second moments, not the previous definition that I said. So this only holds only when I plus j is 0. So the Q00, which is the flux, it's a scalar. It does not depend on the coordinate transformation at all. Even you can stretch the coordinate frames, or you can rotate the coordinate frames. The flux is going to be the same. The Q01 and Q10 are like vectors, because these are the position coordinates. So this is like an xy, a two-dimensional vector. And the higher moments behave like what we call as tensors. So Q00 will not have any A dependence. Q10 and Q01 will have one A in the transformation. The second moments will have two A's in the transformation. So this is how tensors transform under coordinate transformation. But if you don't know what tensors mean, or if you're not comfortable with the transformations, that's fine. But this is how they change. The moments, second moments change under a coordinate transformation. So yes,
S is the order.
Is the original, so what we will call as the source, the moment in the source plane.
Oh, okay.
So Q is the moments in the image plane.
Oh, okay.
So epsilon S will correspond to the true ellipticity. By true I mean the unlensed ellipticity of the galaxy, and epsilon is what you would measure after lensing. Again, by true, it is possible that it's not at all elliptical, the galaxy is not at all elliptical, but from the moments we can come up with this number. So epsilon S is what you would measure if there was no lens, and epsilon is what you would measure if there is a lens. And the relation is given in terms of the G, which is the shear. It's in particular it's the reduced shear, it's not gamma, it's G. So that's why we define G to be the most important quantity here. And if you do, so if you do a binomial expansion, or so if you expand this to infinite orders, you will have all possible terms. But to the first order in G, it's an approximation, which is very, very true in weak lensing, because again the magnitude of G is small. You get a quantity like this. So all that you have is the numerator, or another typical approximation is to just ignore this denominator and then just say epsilon is epsilon S plus G, but that's not a very good approximation. And now we are going to this final part of actually estimating this lensing shear, the G. Yes.
Sorry, just to make sure, the asterisk.
Yes, it's a complex conjugate.
Okay.
Sorry, yes, I should have said that. All these quantities, the epsilons and G's, are complex numbers for that reason, because the formulas are simple. Otherwise, you would have had to do this in real for epsilon 1, epsilon 2, G1, G2. That's ugly. Okay, that's supposed to be S itself. So yeah, that's so I took it from another paper of mine where I had int, and I forgot to change s in both. But yeah, so it's supposed to be it's supposed to be s in both places. Sorry for the inconsistency in notation. I will fix that when I upload the slides. But okay, so what are the unknown quantities here? Epsilon is what we can measure from the image. So it's the lensed galaxy that we can measure. So we know this. G is the lensing effect that we want to find. So we want to know this. So clearly this is unknown. Epsilon S is the true unlensed shape of the galaxy. And again, this is something that we don't know. In micro lensing or lensing by stars, we have moving objects. So you can see them unlensed for some time, you can see them lensed at some time, and then the lens moves away. For example, when we talked about micro lensing, we can have a planet or a star or a black hole causing a lensing for some time and then moving away. So you have this luxury of seeing both unlensed and lensed source for Milky Way objects, stars. But these galaxies are very, very far away. Nothing ever moves there. You can never see a movement in human lifetime. Which means if a galaxy is lensed, it is always going to appear lensed, and there is no way of finding epsilon s. We don't know what G is, we want to find out what G, and all we know is epsilon. So how do we find what this G is? How do we find how much lensing is happening? How do we find these lensing quantities? Okay, take derivatives. How does that help?
Well, you get rid of the epsilon source, then you only have
So you say take d epsilon by dg,
no.
or
No, it's the vector position of the sky.
okay, but how exactly will you change the lensing? You can't go to the lens, which is another galaxy cluster. You can't move the cluster, you can't change the lensing. So d epsilon by dg is not observable.
If you have a cluster,
Yes.
you can measure the elasticity of galaxies far away from the center.
Okay. So the g itself changes with position. So then you are having a different g. So you can't do that either. Or I mean, it does change. It changes smoothly. But the difficulty is, okay, so a different galaxy will also have different epsilon s. So now you are also bringing in different epsilon s. Did I understand your point correctly? So you're looking at a different galaxy at a different distance.
Yes.
Okay, let's assume G remains the same. So G does not have position dependence. Let's assume that for now. But epsilon s, the shape of the galaxy, of a different galaxy, is different. What do we do with that? But you are in the right direction, but what should we do with that? So you now have different galaxies, each with different intrinsic ellipticities, and hopefully the same lensing shear G. You can also measure the ellipticities of all those different galaxies. G is the same. Epsilon changes, epsilon s changes for different galaxies. What can we do with that? So again, we have this full data or a table with each row corresponding to different galaxy. It has its x, y, it has its ellipticity E1, E2, or epsilon 1, epsilon 2. And we will assume they all have the same shear because they are all close by and they are all behind the same galaxy cluster. What next? So remember, these epsilons are complex quantities, meaning their real and imaginary parts can be both positive and negative. Or let's do this the other way. So epsilon is epsilon 1 plus I epsilon 2. So phi is the orientation of different galaxies. Now I have a galaxy like this. 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 If there is no particular direction, what is the average value of epsilon, or what is the expectation value of epsilon? Yes, why? If there is no particular orientation, preferred orientation, so that means galaxies can lie this way, this way, this way, and this way. What is the average ellipticity of all these galaxies? Which means phi can take all possible values. So you have positive and negative values of epsilon 1 and epsilon 2, or in other words, average of this quantity is 0 because it is distributed 0, sorry, yes, thanks. Because it is distributed symmetrically on a circle, on a unit circle, and then average of all these points is 0. So that's what we're going to assume. We're going to assume if you have enough number of galaxies, the sum of the ellipticities is going to be 0, or the average is going to be 0. And that can mean, if I take an average here, so this is the average of the measured ellipticities. I'm going to assume that the average of true ellipticities is 0, so this goes away. I'm assuming that the lensing shear G is the same, so average of G is G, and that's a way of estimating the lensing shear. So all you have to do is to define the ellipticities of galaxies, take an average, and you have the lensing shear. So you've essentially found out how much lensing is caused by a particular lens at a particular place. Now the trick is all these galaxies have to be close enough so that the G at different galaxy locations are not very different. But if the number of galaxies is high enough in a very small region of space, and if you assume G is a smoothly varying quantity, then you should be able to do this, and this is the most simplest way of getting the lensing shear. And again, remember, it's about G, and we have not determined kappa. So we have not determined gamma and kappa separately. We have only determined G, which is the reduced shear. So G was gamma divided by 1 minus k. G and gamma are complex variables. So, and kappa being very, very close to 1, or sorry, kappa being much, much smaller than 1, G is essentially gamma. So experimentally from images of galaxies, you define ellipticities, you can define G or gamma, which is approximately G, and we know this, we have interpreted only this as a geometrical quantity. To get a physical picture, we need to go back to kappa, which has both geometrical meaning and a physical meaning, and that's what the exercise that we are doing yesterday is about. If somebody gives you different values of gamma, how do we get this kappa? Or how, if we have this values of G, how do we get kappa? So that's the mass reconstruction exercise that we are doing, which we will also do again today. But this is essentially to give you some physical or some intuition behind what we are doing. So is the whole picture about kappa, gamma 1 and gamma 2 clear? So we can never get the size of the galaxy. So I said kappa has this physical meaning and geometrical meaning of changing the sizes. But you don't know the original size, and you don't know by how much the size has changed. And size is not a quantity that can average to 0. I mean, it is a positive quantity. But thankfully, ellipticity that we have defined can take both positive and negative values, and we can assume that its average is 0. That allows us to get the shape of the object, but not size of the object. If we could somehow get the size of the object directly, then we don't need to deal with this gamma 1 and gamma 2. But the fact that we don't know anything about the intrinsic or the true nature of the galaxies means that we can only find the shapes, we can only find gammas, and we need kappa to convert it to a physical mass quantity. And that needs some extra work, which is what we are doing in the exercises. But the point is, kappa is not a direct observable in most of the cases, and we need this quantity which only has a geometrical meaning. Is this clear? So this picture tells you how galaxies can all be oriented differently. So this is a very simplistic picture where all galaxies are circle. And now if I take a clump of dark matter which is invisible and keep it in the center, this is how it would look like. This is the unlensed or the intrinsic distribution of the galaxies. Every galaxy is a circle, and you can see this pattern here. So you can see that everything is oriented in a circle. So this roughly corresponds to the Einstein radius of the lens. And the farther away you go, the lesser the coherent pattern that you see. And if all these were perfect circles, finding the length, the G is very, very easy. You can do this for every galaxy. But the fact that you don't know the intrinsic shape, so we call this as the shape noise. The galaxies themselves could have very different ellipticities oriented in different ways. So that essentially means that we can't find the G from one single galaxy, but we need an ensemble of galaxies. We need many, many galaxies so that we can take an average to find G. So that's how it is typically done. So for the strong lensing cases where you can see this for just one particular lens or one particular galaxy, you don't need as many galaxies. But in the weak gravitational lensing where you don't see those strong features, you need multiple galaxies. Typically a weak lensing survey will observe millions of galaxies, or yes, probably millions of galaxies, and then it will measure the shear as a function of position, which is what you have in the data file. So it's shear measured as a function of position. And then we need to convert this to the convergence or kappa as a function of position that can tell you something about the mass density. So that's how you also estimate how much mass is there, how much of invisible mass is there just from the gravitational effects. So that's essentially this field of weak gravitational lensing in summary. It's a very, very difficult field. There are so many other nuances that I have not even told you about. We will talk about some tomorrow, but it's an interesting but a very difficult field. So no wonder that you are having some trouble with the exercises. But is the concept clear? Is it clear with everyone? So this is another way of seeing the same thing in 3 dimensions. So here are these galaxies. So this is the source plane. Galaxies aren't perfectly elliptical, but you can see that they're somewhat elliptical. Again, this is a cartoon picture, of course not a real picture. And then this is a galaxy cluster with some galaxies and this black dark matter around. And if you see this from our point of view, you don't quite see this image. You can see that these galaxies, which are randomly oriented, are now somewhat going in circles around this cluster, galaxy cluster. Whereas that was not the case in the source plane. That is truly not the case. But because we have this lensing object, a galaxy cluster with a lot of dark matter in it, you can observe this pattern. And from this observed pattern, the goal is to reconstruct, is to tell something about the mass of this galaxy, how big this galaxy cluster is, how is it distributed, and so on. So this is something that we are doing in the practical exercises. So that will be the end of the morning session. If you have any questions, can talk about it. If not, we will continue with the exercises from yesterday today. So let's try to finish the exercises and get a kappa from gamma maps. Okay.